Let's do this example 4. So in this example we have a molecule which is called paracetamol. It is an active substance of the medicinal product. It has this formula: C8H9O2N. C8H9O2N. So we are asked to calculate its formula mass in atomic mass units, and to determine its molar mass in gram per mole, and to calculate the mass in grams of a 0.555 mole of this substance, and how many molecules of paracetamol are there in this mass of 0.5 grams of this pain reliever. So we start by determining the formula mass, which is equal to, so the formula mass of the paracetamol, it has this. So we have the atomic mass of carbon times 8 plus the atomic mass of hydrogen times 9 plus the atomic mass of oxygen times 2 plus the atomic mass of nitrogen. Of course, all these are from the periodic table, so they are average atomic mass. So by replacing here with carbon, we have 12, 1, 16 and 14.01. So we get a value of 151.18 atomic mass unit. Now its molar mass, here we have the formula mass for one molecule of paracetamol. Now for its molar mass, which means that the 1 mole of paracetamol, it has a mass of 151.18 grams. Or we can write it like this: the molar mass of paracetamol is equal to 151.18 gram per mole, like this. So here we determined the molar mass from the formula mass, because we said that the molar mass, it has a mass in grams which is numerically equal to the substance atomic mass. Third question: calculate the mass in grams of a 0.55 mole of this substance. So here we use dimensional analysis. So the starting value is, we have a beginning value which is 0.55 mole of paracetamol. So from this value we have to get the mass in grams. So in order to perform the dimensional analysis, we have to understand that we are given a value in mole, that we have to get the mass in grams. So what do we use? Which conversion factor that will help us to go from the mole to the gram? The relationship between mole and gram, it is the molar mass. Okay, so what do we do? So here we have 0.55 mole of paracetamol. We have to multiply by a conversion factor that will give me the grams in the top of this fraction. And here we have this molar mass. This molar mass, I can write it like this: we have 1 mole of paracetamol, it has a mass of 151.18 grams. Or we can write it differently: 1 mole at the bottom of the fraction, 1 mole of paracetamol, which has a mass of 151.18 grams. So which one of them we'll use? Here we have the gram and the mole in the denominator, so we'll use this one. So 1 mole of paracetamol, it has a mass on 151.18 grams. So we can cancel here mole of paracetamol and mole of paracetamol, and we get the mass of paracetamol that correspond to this amount of substance. which is equal to grams. So this value corresponds to the 0.55 mole of paracetamol. Now, the last question, how many molecules of paracetamol are there in 0.5 grams of this pain reliever? So here, the fourth questions, we are given another mass, which is 0.5 gram. We are given a mass in grams, and we are asked to determine the number of objects. Here the objects are the molecules. So here the question is which conversion factor to use to go from the mass to the number of objects. Unfortunately, we don't have this conversion factor, but instead we can add other stages. For example, we can go from the gram to the mole using, we can finish the sentence, the molar mass, exactly. We can use the molar mass to go from the gram to the mole. Now, after having determined the mole, we can go from the mole to the number of objects using the Avogadro's number. So we have to do this stage. So we have here the molar mass of the paracetamol, and here we have the Avogadro's number. So here we start, so we ask to determine the number. So here the number of paracetamol molecule, we start by 0.5 gram of paracetamol. We multiply by a conversion factor that involves the gram and mole. So here we have gram of paracetamol and mole of paracetamol. Here we have 1 mole of paracetamol. It has a mass of 151.818 gram of paracetamol. So we can cancel gram of paracetamol with gram of paracetamol. After that, we know that now we have to introduce the Avogadro's number. We know that Avogadro's number, it is equivalent for in 1 mole. The Avogadro's number corresponds to the 1 mole. So 1 mole of any substance contains this number of objects. So we can write a conversion factor that uses the mole in the denominator and the number of objects in the numerator. So in 1 mole of paracetamol, we know that we have 6.02 times 10 to the 23 numbers of paracetamol. So we can here also cancel mole paracetamol, mole paracetamol. At the end, we get the exact number of paracetamols, or here, at the end we can get the exact number of paracetamols from this equation. So we make the calculation, 0.5 that we multiply by this fraction, and we multiply by this number. So we get 1.99 times 10 to the 21st power molecules of paracetamol. So we have this number, which is a huge number. The magnitude of this number is an extremely large number. It is the magnitude of 10 to the 21st power. So that is the exercise. So from this exercise we could determine the formula mass, and from the formula mass we can easily determine the molar mass, because they are numerically related. After that, we determined the grams that correspond to a number of mole, this amount, using the molar mass, and at the end we use the gram, the mass, and we determine the number by using 2 conversion factors that are the molar mass and the Avogadro's number. Now, what is the relationship between the atomic mass unit and grams? So the atomic mass unit of an atom, C12, represents the mass of 1 carbon-12. So here, the relationship between the mole and the atomic mass unit. So here, the atomic mass unit of an atom C12 represents the mass of one carbon-12. So here, for one isotope carbon-12 atom, we have the atomic mass unit. Okay, it is defined as equal to 12.0 atomic mass unit. So here we have the atomic mass unit. And also the molar mass of an atom C12 represents the mass of 1 mole of C12. So here for 1 mole of C12 atom, we have, so here for 1 mole or in 1 mole of C12, we have a value of 6.02 times 10 to the 23 carbon 12 atom. It is the definition of 1 mole, which represents this number that corresponds to 12.0 grams of carbon 12. Okay, so by here we can get two equations, 1 and 2. We can first write that 12.0 atomic mass unit is equivalent to 1 carbon 12 atom. By making an equality between them, and also here for the second equation that we'll use, we have 12.0 grams of carbon 12. It corresponds to this number of atoms times 10 to the 23rd power of carbon 12 atoms. So here we have 1 atom and here we have 1 mole atom. So by making the consolidation C12 atom, 12 and 12, so at the end we have this 6.02 times 10 to the 23 atomic mass unit is equal to 1 gram. Okay, or we can write it, it's better like it. 1 gram is equivalent to 6.02 times 10 to the 23 atomic mass unit. Or we can write it differently. 1 atomic mass unit is equal to the 1 over 602 times 10 to the 23, like this, in grams, like this. And this fraction is equal to 1.661 times 10 to the minus 24 grams. And this mass represents the 12th of the mass of carbon 12 atom, which is almost equal to the mass of 1 hydrogen atom. The hydrogen atom, it has this mass, it has this mass, 1.6735 times 10 to the 24 grams. So we can see there that 1 atomic mass unit, it has this mass. So it is the relationship between the atomic mass unit and the mass in gram, which is the mass of 1 proton or 1 hydrogen atom. In the last part of this lesson, we are going to talk about the percent composition of compounds. So what is percent composition? The percent composition is the percent by mass of each element in 1 mole of compound. Its expression is as follows. We have the percent of an element, which is equal to n times the molar mass of that element over the molar mass of a compound times 100%. For example, for 1 mole of CHCl3, which has a mass of 119.4 grams, we have in 1 mole of this compound, we have 1 mole of carbon, 1 mole of hydrogen, and 3 moles of chlorine atoms. So from this number of moles we can get the n, the value of n, that we will multiply by the molar mass of the element. So here, for example, for this I will give just the example with the carbon. So we write the, so we have the percent of carbon, percent by mass of carbon. We have, because we have 1 mole of carbon, it means that 1 times 12.01 gram per mole, and here we have the molar mass of chloroform, which is 119.4 gram per mole times 100. So the percent by mass of carbon is 10.06%. And the same thing will apply for the other element. We have 0.84% for the hydrogen and 89.20% for the chlorine. And when we add this 3% by mass of this element, we have to get 100%. Let's do this last example. Example 5. First question. Calculate the percent composition by mass of hydrogen, phosphorus, and oxygen in H3PO4 or phosphoric acid. This compound is used in detergent and fertilizers. So we have this compound H3PO4. So to get the percent by mass of hydrogen, phosphorus, and oxygen, we have first to determine the molar mass of this compound. After that, we can calculate the percent by mass of each element. So here, to calculate the molar mass of the phosphoric acid, as usual, we start by adding each mass of the element. So we have the molar mass of hydrogen times 3 plus the molar mass of phosphorus plus the molar mass of oxygen times 4. And here we have the molar mass of phosphorus is 30.95 gram per mole. Here we get a value of 98.0 gram per mole. Now we can calculate the percent by mass of each element. And before to calculate the percent by mass, as a second step, we have to determine the number of moles of each element. So here, for 1 mole of H3PO4, we have 3 moles of hydrogen, which means that the N is equal to 3. We have also 1 mole of phosphorus, which is N equal to 1, and we have also, for 1 mole of this compound, we have 4 moles of oxygen, which means that the N is equal to 4. So from this we can calculate the percent by mass. We start by the hydrogen. So we multiply the N, which is 3, times the molar mass of the hydrogen, which is 1.01 gram per mole, and on the bottom of this fraction we write the molar mass of the compound, which is 98%, or 98 gram per mole. 98.0 gram per mole. We multiply by 100. in order to get the percent. So we do the same thing with the other. For the phosphorus also, we have to multiply 1 times 30.95 gram per mole over 98.0 gram per mole times 100. We get the percent by mass of the phosphorus, and for the oxygen the same thing. We have 4 times 16.0 gram per mole over 98.0 gram per mole. So here each time we have here the molar mass of oxygen, here the molar mass of phosphorus, and here the molar mass of hydrogen. So by doing the calculation, we get this percent by mass. We have for the hydrogen about 3.1%, for the phosphorus is 31.6%, and for the oxygen is 65.3%. If we add this 3% by mass, we should get 100%. Now let's do the second question. Here we are asked to determine the number of moles of this element, carbon, hydrogen, and oxygen, in 1.5 mole sample of lactic acid with this chemical formula C3H6O3. Second question, we have lactic acid C3H6O3. We can use this abbreviation LA, lactic acid. So here we have given a number of moles of the compound. We have moles of the compound or the lactic acid, and we are asked to determine we have 1.5 moles of, and we have to determine the number of moles of each element for this mole. So the number of moles of H, C, and O. So, but first of all, we have to determine the number of moles for 1 mole. So we know that in 1 mole of lactic acid, we have 3 mole of carbon, we have 6 mole of hydrogen, and we have 3 mole of oxygen. So we can get this, we can write this in another as a fraction. For example, we have for 1 mole of lactic acid, we have 3 mole of carbon. Or we can write it like this also: 1 mole of lactic acid, we have 3 mole of carbon. The same thing here. For 1 mole of lactic acid, we have 6 moles of hydrogen, and for 1 mole of oxygen, it is the definition of the percent composition. 1 mole of oxygen, we have 3 mole of oxygen. So here for 1 mole, we have the number of moles of each element. But now the question is, for 1.5 moles, how many moles of each element in 1.5? So here we start by the first one, the carbon. So here we start by the moles of carbon. So we start by the given value, 1.5 moles of lactic acid. We have to multiply by a fraction. In this fraction, we'll use this one. We'll use either this one or this one. But we should use the one that will cancel the mole of lactic acid. Which one? It is this. Because 1 mole of lactic acid is on the bottom of this fraction. So we multiply by 1 mole of lactic acid. We said that it contains 3 moles of carbon. So we can cancel mole lactic acid, and we can get the number of moles of carbon. So here 3 times 1.5 is equal to 4.5 mole. So for 1.5 moles of lactic acid we have 4.5 moles of carbon. The same thing with number of moles of hydrogen. We have 1.5 mole of lactic acid times, we said that 1 mole of lactic acid contains 6 mole of hydrogen, which is equal to, so here we cancel mole of lactic acid and we get a value of 9 mole of hydrogen. And here, because we have the same number of moles for carbon and oxygen, here without making the calculation we have mole of oxygen, we have 4.5 moles of oxygen because we have the same number. So there are the number of moles of each element for 1.5 moles of lactic acid. The last one, how many grams of nitrogen are present in 0.2 gram of sample of caffeine? The formula of caffeine is as follows: C8H10N4O2. So the last question, we have caffeine and 4O2. So we are given the mass of caffeine, which is a compound or molecule, and we are asked here, the value is given, the number is given of mass of caffeine. We are asked to determine the mass of nitrogen, which is an atom. So unfortunately we don't have a direct way to go from the mass of caffeine to the mass of the atom, but we can instead make some steps. For example, from the mass of caffeine we can get the mole of caffeine, the molecule, and when we go from the mass of caffeine to the mole of caffeine, we can use the molar mass in gram per mole of the caffeine, of course. And after that we can go from the mole of caffeine to the number of moles of nitrogen, which is the atom, using the definition of the percent composition. So we know that for 1 mole here, 1 mole of caffeine, how many moles of nitrogen we have. And from the mole of nitrogen we can go to the mass of nitrogen using the molar mass of nitrogen, which is given in gram per mole. Still here we have the atom. So we start by the compound and we finish by the atom. So we first have to determine the molar mass of caffeine, the number of moles for 1 mole of caffeine, second, and the third, the molar mass of nitrogen, which here it is straightforward because we can get it from the periodic table. But for these two first one, we have to calculate them. We start by the molar mass of caffeine. The molar mass of caffeine, it is calculated from its chemical formula. So we have the molar mass of carbon times 8 plus the molar mass of H times 10 plus the molar mass of nitrogen times 4 plus the molar mass of oxygen times 2. So we get, by making, here we can get the value from the periodic table, and the molar mass of caffeine is 194.19 gram per mole. Now we can write this molar mass in two different ways. Either we can say that 1 mole of caffeine has a mass of 194.19 grams of caffeine, or we can write it like this: 1 mole on the bottom of this fraction, 1 mole of caffeine has a mass of 194.19 grams. Why we did write these two fractions? Because we need them when writing the equation to calculate the grams of nitrogen. So we'll use one of them. The same thing for the mole of caffeine. We have 1 mole of caffeine, which is C6, C8, H10, and 4O2. We have 8 mole of carbon, 10 mole of hydrogen, and 4 mole of nitrogen. The last one, 2 mole of oxygen. Here we are interested in the mole of nitrogen. So here we can write like this: for 1 mole of caffeine, we have 4 mole of this atom, nitrogen. Or we can write this another conversion factor, which is 1 mole on the bottom of this fraction of caffeine contains 4 moles of nitrogen. So also here we need one of them for the equation. And the last one here, the molar mass of nitrogen is equal to, so we have 1 mole of nitrogen is equal to 14, has a mass of 14.0 gram, or 1 mole of nitrogen has a mass of 14.01 gram. So we have all these conversion factors needed to go from the mass of caffeine, which is given 0.2 gram, to finish by determining the mass of nitrogen atom in this mass of compound. So here is the equation. So here with the mass of nitrogen in grams, of course. So we start by the given mass. We have 0.2 grams of caffeine. Here we need to get the mole of caffeine for this mass. We multiply by the molar mass of caffeine. Here the molar mass of caffeine, we have two conversion factors. We'll use either this one or this one, because we have gram of caffeine. So we need to multiply by, here we need to get the mole of caffeine. So we need to multiply by the conversion factor where mole is on the top and gram of caffeine is on the bottom of this fraction. So which one? It is this one. So 1 mole of caffeine, it has a mass of 194. So 1 mole of caffeine, it has a mass of 194.19 grams. Here we can cancel gram of caffeine with gram of caffeine. Now we have to go from the mole of caffeine to the number of moles of nitrogen using this conversion, one of this conversion factor. So here we have to multiply by a fraction or the conversion factor where the mole of caffeine is written on the bottom of this fraction and the moles of nitrogen must be at the top, on the top of this fraction. So here we have, for 1 mole of caffeine, we'll use this one. So for 1 mole of caffeine, we have 4 moles of nitrogen. So we can cancel mole of caffeine with mole of caffeine. And the last one, the last stage, in order to go to the mass of nitrogen, we have to use the molar mass of nitrogen. So we multiply here by a fraction where mole of nitrogen is written on the bottom of this fraction and gram of nitrogen on the top of this fraction. So we'll use one of them here. We have either this one or this one. Here we'll be using this one because we have gram of nitrogen on the top. So we'll use this one. 1 mole of nitrogen, it has a mass of 14.01 gram of nitrogen. Here also we can cancel mole of nitrogen, and at the end we get the grams of nitrogen. We can make the calculation by multiplying 0.2 times 1 over 194.19 times 4 times 14.01, and we get the mass of the nitrogen in this compound, which is equal to 0.058 grams of nitrogen. So these mass corresponds are found in 0.2 grams of caffeine. Nice. So we finished the 3 questions, and to summarize, the atomic mass or given for the atoms is the average of the naturally occurring isotopes of that element. So here the atomic mass given in the periodic table. Also, a mole is an Avogadro number of atoms, molecules, or other particles. Because we used the term objects, so the objects can be anything: atoms, molecules, protons, or other subatomic particles. Also, the molar mass in grams is numerically equal to the mass in atomic mass units and contains Avogadro's number of entities. Also, the percent composition is the percent by mass of each element in 1 mole of a compound.